Have you ever wondered if the universe speaks in a language we are only just beginning to understand, or if the tools we build to simulate reality are merely shadows on a cave wall? For decades, quantum physicists have debated whether analog simulators could ever truly rival the power of universal quantum computers, or if they were destined to remain specialized calculators for narrow problems. Today, that debate has been settled, and the implications ripple far beyond the laboratory, touching everything from the financial markets we navigate daily to the very fabric of how we process information. Welcome to a journey through the latest breakthroughs in quantum science, where theory finally meets practice in stunning fashion. In this video, we will explore how a series of groundbreaking studies has transformed our understanding of quantum computation, proving that analog systems are indeed universal, discovering new ways to measure precision in noisy environments, and witnessing the first successful application of these theories to real-world financial data. Stay until the end because the convergence of these ideas suggests we are standing on the brink of a new era where quantum algorithms solve problems previously thought impossible, reshaping our approach to artificial intelligence and complex system analysis. For a long time, a shadow of uncertainty loomed over the field of analog quantum simulation. The central problem was a question of capability. Could systems like the transverse field Ising model, which describe magnetic interactions in materials, do more than just optimize specific tasks? Or were they fundamentally limited, unable to perform the full range of calculations that a gate-based quantum computer could handle? This wasn't just a technical hurdle. It was a philosophical barrier. If analog simulators were merely specialized optimizers, then the dream of a universal quantum computer running on diverse hardware platforms would remain out of reach. Furthermore, as we attempted to build these machines, we faced the crushing weight of noise and error. Traditional methods for characterizing quantum processes scaled exponentially, meaning that as systems grew larger, our ability to verify their accuracy vanished. We needed a way to navigate this complexity without drowning in data, a method to find clarity in the chaos of qubit interactions and environmental fluctuations that threaten to erase the very information we seek to preserve. But now, a wave of discovery has washed away these doubts. Researchers have proven that the global transverse field Ising model, with non-monotonic time-dependent fields, is polynomially equivalent to the gate model of universal quantum computation. Imagine a key that was thought to fit only one specific lock, suddenly opening every door in the castle. This proof confirms that analog platforms are not limited specialists, but universal computers, capable of performing any quantum algorithm with only polynomial overhead. This resolves a long-standing theoretical ambiguity, showing that with precise control, analog systems possess the same computational power as their digital counterparts. Simultaneously, a new framework called ensemble feature selection has emerged to tackle the problem of noise. Think of trying to hear a whisper in a roaring stadium. Traditional methods required listening to every single voice to understand the message, a task that becomes impossible as the crowd grows. This new approach, however, combines experimental measurements with ridge regression to estimate process infidelity with stunning precision, about 0.01, bypassing the exponential scaling that plagued previous techniques. It allows us to calibrate complex quantum gates on noisy hardware quickly and efficiently, without relying on rigid structural assumptions. Perhaps most excitingly, these theoretical victories have marched out of the abstract and into the real world. The hybrid Q-redo MIS algorithm has successfully solved maximum independent set problems using real financial market data from the S&P 100 and the Nikkei 225. Running on Quantinuum's 98-qubit trapped ion system, this application didn't just work in theory. It delivered success probabilities of 0, 40, and 0. 95 respectively, reducing the time-to-solution scaling by a factor of 3.2 compared to standalone methods. This is the moment the rubber meets the road, proving that hybrid quantum classical frameworks can effectively handle the dense, non-local correlation graphs of our global economy that once stymied standalone optimizers. The implications of these converging discoveries are profound for science, technology, and humanity. We are witnessing a decisive shift from abstract exploration to rigorous, practical application. The confirmation that analog simulators are universal computers expands the horizon of what hardware can achieve, suggesting that we may not need to wait for perfect, error-free machines to begin solving complex problems. Instead, we can leverage the robustness of continuous variable systems and new error correction codes, like the dual-rail CAT code, to build resilient technologies that thrive even in imperfect environments. Moreover, the success of applying these algorithms to financial data signals a new partnership between quantum computing and artificial intelligence. As large language models begin to autonomously translate natural language requirements into executable quantum code, the barrier to entry lowers dramatically. We are moving toward a future where the complexity of quantum mechanics is hidden behind intuitive interfaces, allowing scientists and engineers to focus on innovation rather struggling with low-level programming. This democratization of quantum power promises to accelerate discoveries in fields ranging from material science to drug development, as we gain the ability to simulate nature's deepest secrets with unprecedented fidelity. In summary, today's research has shattered